In the last class we had seen we had studied propositional logic, and we had seen some basic ways of doing reasoning with propositional logic. So, today we will extend the logic further and move onwards to what is called first order logic. So, in first order logic, the main, so what we have done so far is we have seen how to represent a problem in logic, we have seen propositional logic, we will now see first order logic, and then we will finally study how we can do inference in first order logic. Right. So, the difference between first order logic and propositional logic is in the existence of predicates. Now, if you recollect that in propositional logic we had propositions which could take values of either 0 or 1. So, anything that we want to represent is in terms of propositions which have a Boolean value, true or false, right. Now, unlike that, in first order logic what we are going to have is we will have things called predicates, and predicates can have one or more arguments. So, you can have a predicate which has arguments x, y and z, right. Now, there is no truth value that we associate with this predicate as such, but we can always say that for all x, for all y, for all z, I have p x y z. So, then this whole thing has a truth value. So, this whole thing can be true or false. So, if it is the case that for all values that x can take, for all values y can take, for all values z can take, this is true, then this whole thing is true. In other words, when these are like variables, x, y, z are variables. So, if you assign some value to them, now these values need not be numerical, it is some instantiation that we do to these variables, we assign them some value from the domain of these variables, and if we know, or if the knowledge base already contains the fact that for those variables this predicate is true, right, then we say that for that value, for that value of x, for that value of y and for that value of z, p x y z is true, right. Similarly, you can have there exists x, for all y there exists z, p x y z. That means that there exists some value of x such that no matter how you pick your y, there will always be some z which is able to satisfy p x y z. P x y z has a truth value when x, y and z are instantiated to some values, right. So, p of Tom, Dick and Mary can have a truth value, right, but if you just leave them as person x, y, z without instantiating them to any value, then we cannot say whether that is true or not, right. But we can have these quantifiers, and we have two types of quantifiers, namely there exists and for all. I think you are familiar with these things from discrete structures. So, this means that there exists some value of x for all, such that for all values of y there exists some value of z which satisfies p x y z, and it is not difficult to see that the positions of these for alls and there exists y's are, they are not commutative. So, this is not the same as writing for all y there exists x, there exists z, p x y z. though it may be cases where one implies the other, but these two are certainly not equivalent, right. So, we cannot actually move the quantifiers across each other, they will have different meanings, and we will shortly describe a set of things that we can do and we cannot do on this kind of logic. But first thing that we have to understand is how do we actually use this kind of predicates to model actual scenarios. How do we use this kind of predicates to model actual scenarios, and then we will come to the kinds of reasoning that we can do with that logic. So, firstly let us study briefly the syntax of the logic. The syntax of the logic is as follows. We have constants like A5, Kolkata, etc. We can have variables which are usually will be written in short in small capitals, in small letters. We will have predicates like before, has color and raining, and we will have also functions. Now, there is a difference between what we have in predicates and what we have in functions. Predicates, once you instantiate the arguments of the predicate, you have a true or false value, whereas functions can have any value. So, in case of predicate logic, in case of first order logic, your functions can return you values which are numeric, non-numeric, characters, strings, whatever, right. So, they just have a return value. Okay. So, for example, if you want to say that every child loves its mother, right, then we can write it in two different ways. One is, okay, let us see, we want to express the fact that or better still, let us say we want, instead of saying every child, let us say everyone, right. There are two ways in which we can write this. One is we can say that for all x, right, there exists a y, right, such that mother which means that y is a mother of x, right, and right. This is one way of writing. We can also use a function called mother, where given x, mother x will denote the mother of x. So, if we treat this as a function, then we will write for all x loves x Now, see the difference in representation. Here in this case mother was a predicate with two arguments. Here it was a predicate with two arguments. Here it is a function. So, here the value, given the value of x and y, mother x y is true or false. Here given the value of x, mother x gives us another, returns us a value which we can use within the predicate. In first order logic, these functions will never appear except as arguments to predicates. So, these functions will not appear outside any predicates. So, if you look at the syntax of the logic, we will have predicates, and within predicates some of their arguments can use functions. Right. So, let us continue with the syntax of first order logic. So, we can have different kinds of sentences. The first kind is atomic sentence, where we have a predicate. This is a basic form of a sentence, predicate which has a set of terms. The arguments of the predicates are terms, and a term can be a function of other terms recursively, or it can be a constant, or it can be a variable. So, it can be x, which is a variable, it can be Tom, Dick or Harry, which are constants, and it can be a function like we had mother of x. Okay. So, and these terms are the that form the arguments of the predicate. We also have term equal to term as a special kind of predicate. This is a special predicate. This is a predicate which finds out whether these two are equal, right? And if you have this check for equality, we shall see shortly that this is a very important predicate. It is very important to have this predicate. No, see, what we want to check is whether, says I want to find out whether two variables have the same value or not, right. So, I can say x equal to y. So, you can treat this as a predicate which says equal within brackets x comma y, right. So, it is another predicate, but we cannot actually enumerate in our knowledge base the facts associated with this equality. That would be too large. You will have to say this is equal to this is equal to this, like that, right. So, checking for the equality is something which the reasoning system will do internally. So, we just have this special predicate which tests for equality between two terms, right, and returns true if they are equal and returns false otherwise. We will as we progress, you will see that why this special predicate becomes necessary. And then in conjunction with negation, which we had, oops, oh, I missed out the negation. Oh no, I have it here, right. So, here you have, see, you have the negation here, right. So, in conjunction with the negation, you can actually also express term not equal to term, right. So, that is going to be not of term equal to term. Okay. So, the other kinds of sentences that you can have is two sentences with a connective in between, and a connective can be implication or and both ways implication, right, or equivalence. And then we can have quantifier variable, which means there exists x, like that, and you can have several of these followed by a sentence. Right. Then you can have not sentence, and we can also have compound sentences, right. Okay. And we have just two types of quantifiers, for all and there exists. Now, before we proceed further with first order logic, let us understand that why do we call this first order? What would be there in second order logic which is not there in first order? So, here what we are allowing is, we are allowing the quantification over variables. We are allowing quantification over variables x, y, etc. We are not allowing quantification over predicates. We are not saying that there exists a predicate P such that for all x, for all y, P x y. See, this is something which is trying to quantify the predicate itself, right. That is more complex, rather than having well defined predicates and quantification only over variables. So, in this way you can see that we can have a hierarchy of logics, first order, second order and higher order logics, right. We are not going to go into the details of those, but when we study the complexity of first order logic, we will get a glimpse of how difficult it is going to be to reason with higher order logics. But there are actually several tools which enable you to do reasoning with higher order logics. Now, let us do one thing. Let us have a look at some examples and try to formulate these examples in first order logic. So, the first one says, not all students take both history and biology. Right. The first step in solving this kind or modeling this kind of sentences in first order logic is to decide on what is the set of predicates that we are going to have. So, first thing is that it is not that not everybody takes history and biology, not all students. So, there is some predicate which tells us whether a given x is a student, right. So, first predicate that we will define is student x, which says right. Then we can have a predicate which says who takes what subject, takes x y, where which says subject x is taken by y. No, see, these are all variables, right. It depends on what you instantiate them with. These are all variables, right. I actually purposefully used x here to create this confusion. So, this is another variable. This variable and this variable are not the same.
So which is x for student? Which is x for student?
Why? X is just a variable, it is a placeholder. So, if you instantiate x with graph theory, then if you try student graph theory, it will fail, right. If you instantiate x with Angshuman and you have student Angshuman, then that will be a fact that you already have in your knowledge base, right. So, it will match, agreed. So, it depends on what you are instantiating x with. It is these things are like relations, they are, you know, some of the facts and you are trying to use them to derive other facts out of them, right. So, now if we have these two predicates and what we wanted to express was that not all students take both history and biology, right. So, there are many ways to write this statement. One is that we first try to write that all students take history and biology and then negate that, right. So, if we want to write all students take history and biology, then we will write for all x student x implies takes and then put a negation outside the whole thing. The thing inside the negation says that for all x student x, for all x, if x is a student, then X takes history and X takes biology. But what we wanted to express was that this is not the case, that not all students take both history and biology, right. Now note that in this history and biology, these are constants. X is the variable that we have, and the scope of the X is for this whole formula here, right. Okay. Now we can also express this same statement in another form. We can say that there exists a student such that the student does not take history or the student does not take biology, right. So if you want to write that, then we will say that there exists X, student X, and either not takes or and actually these two statements are equivalent. And how do we have this equivalence? If we push the negation in, then the for exists X becomes there exists X, right. And then when you have the negation here, recall that this is of the form A implies B, so that is not A or B, and then if you use De Morgan's to push the negation in, we have student X, and then we have this not takes history X, or this and or becomes this and becomes or, and we have this. Okay. Yes. In the first statement, and no, instead of implication, I mean, how will you connect this? If you do not have this implication, you have to have an and or some connective to connect this. No, I did not, possibly I did not get your question. I mean, you wanted to know that suppose we do not keep this implication here.
So if we had and symbol then.
Okay, let us see. Suppose instead of implication, if we had and here, then we have a problem, because then every X has to be a student, but then every X in the universe is not a student, right. I can always find out some value to instantiate X such that that value is not a student. Suppose I instantiate X to table, and then in your knowledge base you will not find student table. So then what will happen is that this thing will fail. Are you getting me? Instead, what we are trying to say is that if X is a student, then the student takes history or takes biology. If X is not a student, we do not care. That is why we have this implication. In the second case, because we are looking for existential quantification, so we are a priori saying that okay, there exists some student such that the student either does not take history or does not take biology. Clear? Let us look at the second example. Only one student failed history. So now we will have another additional predicate which says failed y, where this says that student y failed in all right. Now, what we want to express is only one student failed history. How are we going to express that? Okay, first thing that we need to express is that there is somebody who failed history. There is one who failed history, and then we will try to also express that only one failed history. So, we say that there exists x and we have student x, there is some student x, right, and failed history x, right, and now we have to express that for all the other students they did not fail in history. To express that only one student failed in history, we have said there exists x who have failed in history, and then for all the other y's they passed history, right. So, we will say that for all y, right, and then not x equal to y, right, and student y, wait, we are coming to that, and student y, this whole thing implies now let us see this once again. We have this tells us that for all y, x not equal to y and student y. So, if y is a student other than this x, then not failed history y, then y did not fail in history. So, if y is a student other than x, then y did not fail in history. Is this all right? So, let us see here. We have this, there exists x, right. So, we are saying that there exists some x who is a student and who failed in history, because we wanted to specify that only one student failed history. Now, that means that 0 students failed history should be eliminated. Huh? No. Then for all y you will not have this. See, if there is more than one person who failed in history, then this is going to fail, because suppose let us say that say Abhik and Suman failed in history, right. Then when you instantiate x to Abhik, right, then this part is fine. Abhik is a student, Abhik failed in history, fine, and then for all y you have to satisfy this, but for all y means that one of those y's is Suman, right, and Suman is not equal to Abhik and Suman is a student, right. Then it should be the case that not failed history Suman, but that is a contradiction because Suman has failed. So, therefore, this is going to fail, this whole thing is going to fail, right. So, this whole statement is going to be true only when there is exactly one student who has failed history.
So in the first part, shouldn't it be student X implies failed history X?
No.
So what if X is not a student?
Then this itself will fail.
So this whole statement will be false. See, it will be database. Like in the previous case.
No, see, this is there exists X. This is there exists X, right. So, for all those X's where X is not a student, this will fail, but if you have at least one X for which this is satisfied, then you are done, right, and that X has to exist because you know at least one student failed in history. So, there has to be at least that person, and that person will satisfy student X failed history X, right. Had this been for all, then your problem would have arisen, but because this is there exists and we are required to guarantee that there exists a student who failed in history. So, this is fine. So, you have to be careful in choosing places where you use and where you use implication. So, when you are looking for existential quantification, when you are looking for the existence of something, then usually you will have scenarios where you have this, there exists X such that this and this and this.
Can we write this for all X?
Let me take it down. For all X,
Bracket
yes,
student X
yes,
and takes history comma X and takes biology comma X.
we do not have biology here at all.
For the first case, we want to write all those students which takes both history and biology.
For all X, let me go back to the previous example, then it is better to write it there. Yes, yes, what is, how do you want to write it? For all X,
A bracket student X and takes history comma X and takes biology comma X.
yes, this is not going to work. I will explain why. Biology, see, that is what we have discussed here actually. Suppose instead of this implication we have this and. See, then because you have for all X here, you are making it mandatory that all X has to be student
X
X.
is not a student X, it will fail.
Yes.
And it is false.
No, but the whole thing will fail because this is for all. So, if it fails for one X, it is going to fail totally because you want this to be true for all X. Had this been there exists X, then if one X is not a student, there can be another X who is a student and can satisfy that. See, this is a for all quantifier. So, if it fails for any X, then it fails totally. If you have a there exists quantifier, if it fails for one X, you can still have another X which is satisfied. If it fails for all of the X's, then the there exists will fail, right. Is that clear? Okay, let us move into a little more complicated stuff. We now want only one student failed both history and biology. Only one student failed both history and biology. So, how are we going to write this? So, let us compare with what we have to do here. I will slightly modify this one here to get the new query.
Whenever there is failed history of X,
No, not exactly, not always. Let us see, here we are looking for a student who has failed both history and biology, and we want to express that there is no other student who has failed both. So, here it will come with and right. I am writing bio in short for biology. So, there exists X, student X and failed history X and failed bio X, right, and for all y x not equal to y and student y means not failed history y or not failed exactly or not failed right. So, this is the query. For there exists X, student X and failed history X and failed bio X, and for all y x not equal to y student and student y implies that either that person did not fail history or that person did not fail biology.
So that is equivalent to replacing history with history and bio.
Where?
If not outside.
Yes, yes, yes. Yes, you can have. If you mean that you can take this not out and have failed history y and failed bio y. Yeah, yeah. That means just moving these two negations out. So, and using the De Morgan again. Yes, you can always do that. Right? Next example. The best score in history is better than the best score in biology. Now, how do we express score? Yes, we here is a case which seems at first glance, and indeed so, it appears that we need a function, right, a function which is going to return the score, because score is something which is not a, it is not a true false value, it is some numeric value that is going to get returned. So, we will introduce a function, and the function will be as follows. The function will be score. The first argument of the function will be a subject, and the second argument will be the student. So, given the subject and the student, this function will return the score obtained by that student in that subject, right. Now, what we want to express is the best score in history is better than the best score in biology. What function? Right. So, we need another function which compares two scores and tells us which is greater and which is less. Now, but that is a predicate, right, it is not a function, because if comparison is going to return you a true or false value, right. So, let us add this predicate, and this predicate right. If we have these two, then let us try to see how we can write this. Now, what we want to express is the best score in history is better than the best score in biology. So, there are many ways to write this. One way to write this is say that we say that okay, if we have an X who is a student and who has taken biology, right, let X be a student who has taken biology, then there exists a Y, a student Y who has taken history, and the score of Y in history is greater than the score of X in biology.
It will be for all students who have taken.
No, if you can do this for all X, then we are done, right. So, let me write down the first this thing. So, what we want is for all X, student X right and takes biology X, right. So, this is says that for all X who is a student and who has taken biology implies there must exist some Y, student Y, and right. There must exist a student of history. So, for every student of biology there must exist a student of history who has scored more, right. So, greater and here we will use the function score, yes, history Y right, and this is from here to here. Let us study this again. What we have expressed is that for all X who is a student of X and takes biology, there exists some student Y who is a student of history and has a score in history which is greater than the score of X in biology, right. So, this is to express the this thing that the best score in history, best score in history is greater than, yes, best score in biology. So, all scores in biology, best score in bio, and effectively what this is expressing is all.
In which the first one is there exists then such that student X and takes biology X. The second one is that there is exist Y such that student Y and takes history Y, and the third one is that greater score history Y and score biology Y.
Now, come again. What? How do you want to write this?
These three terms which will be ANDed, and the first one without overall X it will be there exists X.
Okay, let's see. Let me rewrite this. Okay. So, you are saying first term will be there exists X, then
Student X and takes biology X.
student X and takes biology X,
And there exists Y.
instead of this implication you have and there exists Y, the rest is similar. So, let me get it right. What you want here is that instead of this implication you want and, right.
Yes, their existence.
instead of
For all x, we will have their existence.
here.
Yes, sir.
So, if you write this, so let me get it right. You want this to be changed to there exists x, and you want to replace this by and. Is that right? Huh? No, no, because this is going to get satisfied when any student of history scores more than any student of biology. See, this is going to be satisfied when any student of history scores more than any student of biology.
So this would establish best score greater than least score.
Yes, yes, right. But it does not express the intent that the best score in history is better than all scores in biology. Just think it over. You have to spend some time in digesting the logic, and you have to try writing out a few more statements yourselves to get the hang of things. And it is good to debate on what are the different ways to write the same property and whether we can actually write one property in many ways. Okay. No person likes a professor unless the professor is smart, right. So, try writing this out. No person likes a professor unless the professor is smart. Instead of no person, just make it no one. No one likes a professor unless the professor is smart. So, when you say no one, then you just will not have to write that person x, right. So, how are we going to write this? Okay, so we will have predicate professor, professor x, and we will also have a predicate which says likes x y. Okay, let us clarify this. This says that y likes x, it could be x likes y also. So, you have to specify that what is the semantics of your predicate. Then for all x, right, we will need also a predicate called smart of x, which says x is smart. Professor x says x is professor, smart x says x is smart, right. For all x, professor x and not smart x implies for all y yes, which is fine with us. If x is not a professor, then we do not care whether y likes x or not, right. So, if x is not a professor, then this thing is going to become vacuously true. This is going to become vacuously true.
But if we remove that for all x,
if you remove the for all x and just leave it like this, you have to define some quantification on x, right. Otherwise, it remains ambiguous. It remains ambiguous whether x is quantified, I mean whether you want this to hold for all or you want some x for which you want this, right. So, unless you specify this, you have not completely specified the statement. But later on we will see that that usually the default we will use for knowledge bases is for all x. If we do not specify anything else, we will use that. Okay. Right. Now, Now, look at this last one, please take this down. This is these statements are actually from the book of Russell and Norvig. This is one of the exercises given in that book. Politicians can fool some of the people all the time, and they can fool all of the people some of the time, but they can't fool all the people all the time. Please take this down. Politicians can fool some of the people all the time, and they can fool all the people some of the time, but they can't fool all the people all the time. Fair enough. So, try to write this down in first order logic, assume the proper predicates, etc., right. Okay. We will conclude this lecture with one very famous paradox, which is called Russell's paradox, and this is a very famous paradox which says that there is a single barber in town. Those and only those who do not shave themselves are shaved by the barber, and then the question is, who shaves the barber? Because if the barber shaves himself, then by this statement it says that the barber does not shave himself, because if the barber shaves himself, then he is not shaved by the barber, which is a contradiction. And if the barber does not shave himself, then he has to be shaved by the barber, which again is a contradiction, right. Now, if you try to model this in first order logic, let us see what happens. So, first thing we have to express is there is a single barber in town. So, there exists X and for all y x not equal to y, which is not of x equal to y, this implies right. So, this expresses the fact that there is only one barber, there is only one barber. And then the second statement says that for all x, if it is the case that x does not shave himself, then and only then, so we have both ways implication, x y and right. Now, where is the problem in this? Now, the problem here is that, see, this y, this barber, this person is also in the domain of this x, right. This person is also in the domain of this x. So, that this person is also a member of the town, right. Now, unless we encode that, once we encode that, then we will see that the three together cannot be satisfied anymore. So, there has to be the inconsistency is in this clause, which says those and only those, slides please, yes. Here you have those and only those who do not shave themselves are shaved by the barber, and these those other than the barber, right. So, this those actually it can take values from the entire domain of the town, but then we, unless we exclude the barber from that, there is an inconsistency in this specification, right. So, in the next lecture what we are going to do is we will start formalizing the inference mechanism that will go with first order logic. Today what we have seen is what is first order logic and how we can write out different sentences in first order logic. From the next class onwards we will start studying the inference procedure in first order logic. I had introduced first order logic in the last lecture. So, from this lecture we will start studying the mechanism of inferencing in first order logic. We will see how we can deduce new facts from the existing ones using first order logic. Now, just to do a brief recap, the difference that we saw between propositional logic and first order logic was that in first order logic you can have predicates which have arguments. These arguments can be instantiated with values from a given domain, right, and we can have quantifiers which says that whether there exists a member in the domain which can satisfy the predicate, which is there exists the variable for that predicate, or it could be an universal quantification which says that for all values of the variable x from its domain the predicate is satisfied, right. So, it is the existence of these quantifiers which makes inferencing in first order logic more difficult than that of propositional logic. In propositional logic we saw that we can reduce the inferencing problem to an equivalent SAT problem, a problem of Boolean satisfiability, and we have different Boolean satisfiability solvers which can solve this. But when we go to first order logic, we the domains of these variables can be very large and could be potentially infinite also, and therefore it is not so easy to reduce the problem to a SAT instance. So, let us see some basic things that we need to do in first order logic. Firstly, we need to have some basic inference rules. What can we deduce from what? So, the first of this is universal elimination. Universal elimination says, for example, that if we have for all x likes x ice cream, right,